In this video, we're going to be discussing titrations, which are basically just controlled reactions in which we try to find out something mole related about a substance that we didn't know previously. Again, we're not going to do any math for this. We'll save the math for class, but you do need something to write with, you need something to write on, and once you have those things ready, let's go. All right, so we should probably start off by talking about what a titration is and the different components of a titration, right? So a titration is just a stoichiometry experiment. What we're doing is we're going to very slowly add one substance into another until we get an exactly completed reaction, right? There are two substances that we have to work with. The first component is what's called the analyte. The analyte is the thing that we know the exact number of moles of, right? So for example, in one of our titrations that we're going to do for acid-base, we're going to use a solid potassium hydrogen phthalate. Because we can find the molar mass of that substance and because we can measure its mass to a very accurate degree, we'll know precisely how many moles there are in our reaction to start off with. The titrant, which usually is the thing in the burette, is what you're going to add to the analyte. This is usually the thing or the solution that we want to know something about. So in our example with the KHP, you'll be dropping in sodium hydroxide. The reason why is because we want to calculate the concentration of the sodium hydroxide solution so that we can use it as a standard solution in future labs. All right, so we have analyte, the thing that's usually in the flask. It's what we know the most about. And the titrant, which is the thing we're reacting it with, usually adding it from a burette 1 drop at a time until the reaction's done. All right, so like I said, one of these substances, because we know the number of moles of it, is what we consider a standard. We have what are called primary standards, which are things that we know the number of moles of directly. So that's, for example, something like KHP. We also have secondary standards, which are things that we figure out their molar amounts or concentrations by reacting them with a primary standard. So that would be your sodium hydroxide solution. All right, so that's basically what a titration is. Now, here's how we go through and do it. So what we have is we basically measure out the amount of analyte we want to use. Basically, like the way we'll do this is we'll have a rough idea of what the concentration is in a burette. So say, for example, we think the concentration is about 10th molar. I'll say, okay, if it is exactly 1/10 molar, how much of my analyte would I need to react with, say, 25 milliliters of my titrant? And then I'd calculate that, put that in my flask. I'd add a little bit of water to dilute it. The amount of water you put in the flask is irrelevant to the titration, right? The number of milliliters of water will not affect the number of moles of analyte. That's already been predetermined. So you add enough water so you get a good reaction. You can actually see the change take place around the end point of that titration process. Right? Then what we do is we open up the burette so that we drop 1 drop at a time, like 1 drop every 5 or 10 seconds, into our reaction mixture. We swirl it constantly so we can make sure the reaction's continuing, and we keep adding it very slowly, 1 drop at a time, until we get that perfect stoichiometrical ratio, which is what we call the equivalence point, right? So when the reaction is exactly balanced between the two reactants, that's when we stop. From there, we'll measure the volume of our burette at the end, right? Usually you start your burette at 0 for the first trial, and we'll measure the volume at the end. That will tell us the volume of titrant we've used. And based on the volume of titrant and the amount of moles of analyte and the balanced chemical equation, we can do some stoichiometry and figure out the final answer that we're actually looking for. Now, this leads us to a question now, right? We're going to add 1 drop at a time until the reaction's finished. But how do we know when it's finished? Most substances we react are going to be clear, right? Like if I'm doing a hydrochloric acid sodium hydroxide titration, I produce salt water. That's a perfectly clear solution. How do I know when I'm done? Well, the way that we'd know we're done is that we use an indicator. Indicators are substances that change color at or around the equivalence point. And by around, I mean plus or minus like 1 or 2 drops. The 3 most common ones that we're going to use for our acid-base reactions, we're going to use phenolphthalein. Right? Phenolphthalein is colorless in acidic solution. pink in solution with a pH above about 8 or 9. We have starch. I say it's used in iodometry, so we basically do like the starch potato thing, where when starch is exposed to iodine, the iodine turns dark blue. Right, so that's what we can use as an indicator. And in fact, in our bleach titration we're going to do as a lab, we're going to use starch as our indicator. The other thing you can do, and this is really common amongst some redox reactions involving transition metals, is you have what's called a self-indicator. What this means is that one of the reactants will change color once you reach the equivalence point, and you just wait for that color change. Right, so this is the most common way that you're going to work with reaching equivalence. A couple of other common ways that you can do it, one we'll actually do as a lab procedure towards the end of the year, is we're going to graph. We can graph volume versus pH for acid-base reactions. And what we'll look at, and I'll show you in the next slide, is that there's going to be a rapid rise. The center of that's going to be our equivalence point. Now, if you're doing things that produce precipitation or basically anything that will remove ions from solution, so like for example, if a reaction forms water, you can actually do volume of titrant added versus conductivity. And I'll show you an example of that in the next slide, right? So what we have coming up are a bunch of different indicators. On the left, we have phenolphthalein. Like I said, colorless in acid, go above a pH of 8 or 9, it turns pink. For phenolphthalein, the paler the pink color you get, the better. That pink right there isn't bad, but you could do a lot better than that. The middle upper box is our starch indicator. On the right, we have the starch added. That's basically what's called the triiodide ion, the yellow one on the right. So when you have triiodide, the starch doesn't activate, it remains colorless. The triiodide ion's yellow color takes over. But the moment you form elemental iodine, I2, it will react with the starch and form that dark blue color that you're familiar with. The set of flasks on the right is an example of a redox titrant or redox indicator. This is actually permanganate ion, so potassium permanganate. What happens is when you first add permanganate into the reaction, the permanganate, which is a purple colored solution, will turn into manganese 2. That manganese 2 is what's going to be brown. And as you shake and as you swirl it initially, that brown color will go away because you're going to keep reacting it out. Now, once you get to equivalence, what happens is when you add that permanganate in, the manganese has nothing to react with. It has nothing to reduce its oxidation state down from +7 to +2. So it's going to stay as its purple color, and diluted in solution, it will look kind of pinkish. So that's how you can tell when that's done. Bottom left, we have our pH graph, right? So our pH graph is just volume of base added versus, in this case, the pH. So if you can see on the right-hand side near the center of the graph, how you have that rapid jump from a pH of 4 to a pH of about 13. That jump takes place over the distance of about 2 or 3 drops of solution. So what we'll do is we pick the center of that rise, and that's our equivalence point, because that's like exactly where equivalence happens. And the one on the bottom right, we have a conductivity titration. This is also acid-base, right? We add hydrochloric acid, we add sodium hydroxide to a hydrochloric acid mixture, and what happens is as it reacts, the proton from hydrochloric acid and the hydroxide react to form water. Now, the astute among you may have noticed that we haven't actually changed any of the concentrations of ions, because while we're taking out the proton to form water, we're adding sodium in its place, right? So the concentration of ions isn't going to change. What does change is the volume of solution. So if we have the same concentration, but we increase the volume, conductivity goes down. Now, once we reach equivalence, as we add our sodium hydroxide, there's no proton to react it with. So that means we're adding now 2 ions per addition of base instead of just replacing one of them. So adding more ions in causes the conductivity to rise. We look for the minimum in this graph, and that's our equivalence point. Okay, so this is titration. We're going to work with a bunch of these different calculations in class and how to read graphs, and we'll do multiple titration labs this year. I mean, just off the top of my head, I think we're going to do about 4 or 5 different titration labs at some point in the year. All right, so that is our titration video, or I should say our intro to titration video, and we will see you guys in class.